if the differential equation is not exact, it may be possible to make it exact by multiplying it by a special function. Hello and welcome. I am Dr. Geraldina Fernandez, Associate Professor, Department of Mathematics and Statistics, the Bhopal School of Social Sciences. Dear learners, in my previous lecture, I have discussed about exact differential equations. So now, in this lecture, I will be discussing about those equations which are not exact but can be made exact by multiplying it by an appropriate function. So before moving on, let's first have a look at the topics that would be covered in today's lecture. In today's lecture, we are going to discuss about integrating factor, equations which are reducible to exact differential equations. Now here we will discuss method 1, that is rule 1 for finding integrating factor that would in turn convert it into exact differential equations, and for better understanding of the topic we will solve few examples. So let us first define integrating factor. So if the differential equation is of the form m dx plus n dy is equal to 0, where m and n are functions of x and y and is not exact, it may be possible to make it exact by multiplying it by an appropriate function, say f of x comma y. Such a function is called as an integrating factor for the given differential equation. The number of such functions can be more than 1. So let us understand the definition of integrating factor with the help of one example. So consider the differential equation 2y dx plus x dy is equal to 0. Now first step is to check whether the given first order differential equation is exact or not. So for this we will compare it with the standard form of exact differential equation, which is m dx plus n dy is equal to 0. So on comparing, we will get the value of m as 2y and the value of n is x. The coefficient of dx is m and the coefficient of dy is n. So here m is 2y and n is x. Next step is to differentiate m with respect to y. So while differentiating m with respect to y, we will get 2, and we have to differentiate n with respect to x, that is 1. So clearly the value of del m upon del y is not equal to del n upon del x, which states that this equation number 1 is not exact. However, if we multiply the given equation by x, on both sides, the new equation obtained will be 2yx dx plus x squared dy is equal to 0, which we can mark as equation number 2, is an exact differential equation. We can also test this. So here the value of m dash is 2yx, whereas the value of n dash is x square, while comparing it with the standard form of first order differential equation. So while differentiating m dash with respect to y, we will get 2x, and differentiating n dash with respect to x, again we will get 2x, since we are differentiating it partially. So clearly del m dash upon del y this time is equal to del n dash upon del x, which states that however if we multiply the given equation by a suitable factor, by a suitable function, the new equation obtained becomes exact, as the LHS of the given equation is the total differential of x square y, which on integration gives the required solution. So thus we can say that x, which was multiplied with the whole equation number 1, is the integrating factor. So I hope you have understood the concept of integrating factor. Next, so now sometimes an integrating factor can be found merely by inspection. Here we have a list of exact differentials which help the students in finding the solution. Few of them I have mentioned here, like the total differential of xy is equal to x dy plus y dx. Similarly, the total differential of x by y is equal to y dx minus x dy by y square. Third, the total differential of y by x is similar to the second part, that is equal to x dy minus y dx divided by x square. The fourth one is the total differential of x square by y is equal to 2yx dx minus x square dy divided by y square. So, here basically we are using the quotient rule of differentiation, and last one is the total differential of y square by x is equal to 2xy dy minus of y square dy divided by x square. So, these are few integrating factor which are helpful for the students to find the solution. Now, let us understand the integrating found by inspection with the help of a following example. So, question number 1 is solve x dy minus y dx plus 2x cube dx is equal to 0. So, the first step is, you can see that here dx is appearing in the second as well as in the third term. So, first step is to take common from second and first term, dx we can take common. So, we have 2x cube minus y dx plus x dy is equal to 0, which you can compare it with the standard form of exact differential equation, which is m dx plus n dy is equal to 0. So, here m is 2x cube minus y as well as n is x. So, while differentiating m with respect to y, we will get minus 1, and here differentiation of n with respect to x is 1. So, you can clearly see that del m upon del y is not equal to del n upon del x, which implies that this equation number 1 is not exact. Equation 1 is not exact. So, here clearly equation 1 is not exact, but looking at equation number 1, for the first two terms x dy minus y dx, if we divide this whole term by x square, then it becomes x dy minus y dx divided by x square plus this 2x cube dx will also be divided by x square is equal to 0. 0 divided by any number is 0. So, for the first term we can see that here we have the formula for total differential of x by of y by x, this part we have already done. So, total differential of y by x is x dy minus y dx upon x square. So, we are using the same formula here, and we will have total differential of y by x plus here this gets cancelled and we have 2x dx is equal to 0. So, while simply integrating we will get the required solution. So, therefore, here for this given differential equation 1 upon x square is the most suitable integrating factor for the given differential equation. Next, moving on to the rules for finding integrating factor. So, rule number 1 states that when mx plus ny is not equal to 0 and the equation is homogeneous. Now, what do you mean by homogeneous? By homogeneous differential equation we mean that the degree of each term is same. So, only those differential equations wherein the degree of the variable are same, they are called as homogeneous differential equation. So, we have an added condition that mx plus ny should not be equal to 0. So, then the integrating factor for the given differential equation will be 1 upon mx plus ny. So, if you have an homogeneous differential equation as well as mx plus ny is not equal to 0, then for those differential equations the best integrating factor is 1 upon mx plus ny. Now, let us understand this rule number 1 with the help of an example. For better understanding of the concept, let us solve few questions. So, question number 1 is solve x square y dx minus of x cube plus y cube dy is equal to 0. So, first we will write the given equation, that is x square y dx minus of x cube plus y cube dy is equal to 0. So, first thing is you will have to check whether the given differential equation is homogeneous or not. So, for homogeneous, first we will have to check the degree of each term of the differential equation. So, here talking about the degree of the first term is 3, the degree of the second term is also 3, the degree of the third term is again 3. So, since this differential equation has degree 3, so therefore, this is a homogeneous differential equation. So what we will do, we will mark this as equation number 1, and then here first step is to write the value of m and n. So we can compare it with the standard form of exact differential equation, that is m dx plus n dy is equal to 0, where m and n are functions of x and y. So on comparing it with the standard form, the coefficient of dx is taken as m and the coefficient of dy is taken as n. So here m will be how much? M will be x square y, and n is the coefficient of dy, that is minus of x cube plus y cube. Second step is to partially differentiate m with respect to y and partially differentiate n with respect to x. So the first step was to write the value of m and n, and the second step is to differentiate m with respect to y. So here the function is x square y. Since we are differentiating partially with respect to y, therefore here x square will be treated as constant and partial differentiation of y with respect to y will be 1. So here the value of del m by del y is x square. Now the value of del n upon del x, here we will differentiate n with respect to x. So minus of, we will have del upon del x of x cube plus del upon del x of y cube. So on differentiating it partially, the differentiation of x cube with respect to x will be 3x square by power rule plus differentiation of y cube with respect to x, and here we are partially differentiating, so that will be 0. So the value of del n by del x is minus 3x square. Now you can clearly see that the value of the derivatives del m by del y and del n by del x, they are not same, they are not equal. Therefore this implies that equation 1 is not exact. So since del m by del y is not equal to del n upon del x, therefore we can write it as, therefore equation 1 is not exact. Now we have various rules to find out the integrating factor, which in turn can make this not exact differential equation into a exact differential equation. So here as you can see, equation 1 is of homogeneous form, as well as the value of m x plus ny. Here we will calculate the value of mx plus ny. If it is not equal to 0, as well as the differential equation is homogeneous, then we can apply rule number 1. So now we will have to substitute the value of m and n. The value of m is x square y. So here we have x square y into x plus minus of minus x cube plus y cube into y. So on multiplying it, we will get x cube y minus of, here we will have x cube y and minus of y raised to the power 4. So we can cancel the like terms. Here we have x cube y as we are having the opposite sign. So final value of mx plus ny is minus y raised to the power 4, which is not equal to 0. So since equation 1 is homogeneous, as well as the value of mx plus ny is not equal to 0. So this is the favorable condition to apply rule number 1. So now here we will apply rule 1. Now according to rule 1, first step is to find the integrating factor. So next we will find the integrating factor. So integrating factor can be written as if, and the value is equal to 1 upon mx plus ny. Here we have already calculated the value of mx plus ny. So we will substitute it, and that is minus y raised to the power 4. So therefore integrating factor for the given differential equation is minus 1 by y raised to the power 4. Now the next step is to multiply this integrating factor, on both sides of equation number 1. So as our equation number 1 was x square y dx minus of x cube plus y cube dy is equal to 0. We are going to multiply the integrating factor on both sides of this equation number 1, and that integrating factor is minus 1 divided by y raised to the power 4. So, next is we are going to multiply it. So, here we are having minus 1 divided by y raised to the power 4, and then again we have minus 1 divided by y raised to the power 4. So, we can write it once again. So, this was the differential equation x square y dx. We are multiplying it by minus 1 divided by y raised to the power 4 minus of minus 1 y raised to the power 4 into x cube plus y cube dy is equal to 0. So, on simplifying we will get a negative sign, minus of x square, this y and y will get cancelled and we will have a y cube dx, minus and minus will become plus, and while multiplying it with the second term we will have x cube divided by y raised to the power 4 plus, simplifying this we will get 1 upon y dy is equal to 0. So, this is our new equation. We can mark this as equation number 2. Now, we will test whether the given differential equation is exact or not. So, again we will compare it with the standard form of exact differential equation, which is m dx plus n dy equal to 0, and the coefficient of dx is m, whereas the coefficient of dy is n. So, here m will be the coefficient of dx, this will be m, and the whole bracket will be n. So, next step is to write, we can denote it by m dash and n dash also. So, because we have already denoted the coefficients by m and n, so it is better that we denote it by m dash as well as n dash. So, here m dash is how much? M dash is minus of x square by y cube, and the value of n dash is x cube divided by y raised to the power 4 plus 1 upon y. So, again the step goes the same way. Now, we will differentiate m dash partially with respect to y, treating x as constant. So, here we have minus of del by del y of x square by y cube. So, since we are partially differentiating the given function with respect to y, so here x will be treated as constant. So, this would become minus of x square into del by del y of y raised to the power minus 3. So, here we are using the formula for power rule. So, this becomes minus x square into minus 3 raised to the power minus 4. So, finally, we are getting 3x square by y raised to the power 4. So, this is the value of del m upon del y. Now, we will check whether the del m dash by del y. So, we will check whether del n dash by del x is also having the same value or not. So, here the value of n dash is x cube by y raised to the power 4 plus 1 upon y. So, we are differentiating it partially with respect to x. So, the function is x cube by y raised to the power 4 plus 1 upon y. Now, here using the rule of, we have the derivative of sum of two functions is equal to the sum of the derivative of the two functions. So, x cube by y raised to the power 4 plus del upon del x of 1 upon y. So, here we are differentiating with respect to x. So, 1 upon y raised to the power 4 is treated as it is, and we are differentiating it with respect to x. So, 3x square plus differentiating 1 upon y with respect to x partially. So, this will become 0. So, the final value of del n dash upon del x is 3x square by y raised to the power 4, which is same as the value of del m dash by del y. So, this is same as del m dash by del y. So, now we can write that therefore, equation number 2 is exact, since it is satisfying the condition that the value of del n dash by del x should be same as the value of del m dash by del y. So, the last step is to find the solution of this equation number 2. So, therefore, the solution of equation number 2 is, now we have a formula for this that we have already discussed in the previous lecture, that is integration of m dash dx treating y constant plus integration of n dash. Now, we will consider only those terms which are free from x. So, terms free from x dy, here treating it as x as constant, is equal to c. So, now we will substitute the value of m dash and n dash. So, the value of m dash is that is minus x square by y raised to the power 3 minus of x square by y raised to the power 3. Here we have to treat the integral as y as constant dx, plus from n dash we will consider only those terms which are free from x. So, look at n dash, here the first term is not free from x, whereas the second term is free from x. So, here from n dash we will take only 1 upon y. So, integration of 1 upon y treating x as constant dy is equal to c. Okay, so now we will substitute the value of m dash and n dash. So, m dash here is minus x square by y cube dx, and we treat this integral, we integrate this with respect to x treating y as constant, and next we will substitute the value of n dash. Now, we will consider only those terms of n dash which are free from x. So, here we can see that n dash is x cube by y raised to the power 4 plus 1 upon y. So, from this here we will have two terms, we will consider only those terms which are free from x. So, first term is not free from x, whereas the second term is free from x. So, here the value which we will substitute is 1 upon y. So, integration 1 upon y dy is equal to c, and for this integral we treat x as constant. So, since here in the first integral we have to treat y as constant, so minus 1 upon y cube can be taken out of the integration, and then we have x square dx, plus since we have no x over here, so we have to simply integrate it with respect to y, and c is the constant of integration. So, with the help of power rule we will get minus 1 upon x y cube into x cube by 3 plus integration of 1 upon y is log y, that is equal to c. So, or just simplify it, we will get minus x cube upon 3y cube plus log y is equal to c. So, this is the solution of the given differential equation, in which we have applied rule number 1. Why we have applied rule number 1? Because the given equation was homogeneous, as well as it satisfied that mx plus ny is not equal to 0.